we have the camera set up here, and my TA is going to hold it for us. And so you can see the difference. Here we have single polarizer, two polarizers. Change the rotation, you see it's getting darker and blocking it, right? So that's what a polarizer does. Now, that is not all a polarizer does. There's lots of cool things. So this here is another strip. And I'm going to put this strip of polarizer on here at like a 45-degree angle. Should be blocking some, right? Put the other polarizer on. I have them set up so it should be blocking all of the light, but where the middle one is, it's not. Why would the middle one make it so light gets through? Clearly the bottom one's blocking horizontal, second one's blocking vertical. How's the middle one getting light through? Magic! That's a good answer. Good answer.
It's blocking at a different angle, and so therefore the angle that it's in line with the one it's letting through.
That's exactly right. When we talk about quantum physics, we use this as an example. By putting that second one in, we actually changed the nature of the light. Because it took light that was only this direction and said, well, there's a component. Okay, I'll go vertical. Took light that was only this direction, said, well, there's a component like this and a component like this. I'm going to block this component, but allow this one through. So now the light's like this. And then I block all the light except for what's like this. Well, this has a component that's horizontal that can still go through. So that's kind of cool, but that's not the only cool thing. There's lots of cool things with polarizers. So let's go to this here. This is, there you go. It's simply tape on glass. Really non-exciting. What do you see there in the picture besides that it's out of focus? It's supposed to be the Union College clock tower that's been torn down long before I arrived. That's what it's supposed to be. Now I'm going to put a polarizer underneath it. Is that special? Okay, I'm with you. That's not special. Now I put a polarizer on there. Now we have, it's kind of hard to see. Is there any way to focus this? Is that? No. Yeah, thank you, Windows, for focusing so nicely. It's a blue moon on a white sky. It's not right. What was that? There, that's much better. Now we have a white moon on a dark sky. How's this working? I have people taking organic chemistry. A few of you. Do you remember studying about molecules that rotate the polarization? The cellophane is rotating the polarization. And since different colors have different wavelengths and different indices of refraction, you actually have different rotations for different colors. And so I'm allowing only the light that rotated by 90 degrees through. And that's how the different colors are selected. Well, of course, this one here is my favorite because I like my beautiful cyan and yellow and black flag. Of course, how can I fix the colors? And there we have a much nicer looking flag. And if you could actually see it, in focus, it would look even better. So that did not focus any better. Let's just say that Microsoft didn't put the money into a good camera on their Surface Pros. I'm not done yet. There's more cool stuff with polarizers. So, now this is my last trick, sadly. That is a very important letter because it's the first letter of my name. This is a calcite crystal. Everybody knows calcite, right? Put the calcite crystal on there. And now what do we see? Oh my goodness. Maybe you should just come up here? Seriously, come on. Is there any way in the world to make this thing focus? Yeah, Anybody see focus anywhere? I don't. Well, God bless them. Yeah, if it's an iPhone, that focuses it, right? Not so much with Microsoft in there. Okay, stop bashing Microsoft. Okay, he's bringing at least. Yeah, you really can't.
Making it worse.
Okay, let's just take that off. Come on up here so you can see. Because actually, keep
it open.
Yeah, because that way this here at least you can see it. Up there you can't see anything. So if you look in there, let's see. You're going to be my answer person, Brandy. When you look in here, can you see two R's?
Oh, yeah.
Okay, so we have two R's. Why are there two R's?
Because double R's are better.
Because it's a Rolls Royce now. Now, if I rotate this, notice what happens. One R stays the same position, one moves. We say that it has an ordinary and an extraordinary axis. You have two different indices of refraction based on the polarization of the light. So I'm going to put the polarizer on top. Now how many R's do we see?
One.
And if I rotate it, I can select each one. Which, of course, tells us, yeah, it's two different indices of refraction depending on the polarization direction. Is that cool or what?
Yeah.
See, I love physics. That's what I need you for. So, thank you. So now let's learn something about that. Instead of just saying, ooh, that is so cool, let's learn a little about what's happening. So we know that according to the wave theory of light, we have electric waves and magnetic waves that are working together so that the electric field is always perpendicular to the magnetic field and the direction is perpendicular to both of those. So the light that's coming from, like I said, the projector has some electric fields that are oscillating in the horizontal direction, some that are oscillating in the vertical direction. And so we say it's unpolarized. These pictures, of course, are just showing plane polarized. Plane polarized is the technical term here because there's things like circular polarization. How many people have gone to see a 3D movie where they give you these glasses? How many people like me take them home every single time? I paid $2 for these. They're staying with me. I can use them for physics. Has anyone had me play with these with you before? I think I did in the physics tube too, didn't I? Okay, it's totally cool. Who wants to be my demo person? Okay, George. I first noticed this when I went to the bathroom during a movie. I looked at myself in the mirror. When you look at me, Jordan, what do you see in my eyes?
Kind of different.
It's kind of different. When you look in the mirror, it'll look like your eyes are flickering. And I'm like, what the heck? So now do this. Close one eye and look at my eyes. What do you see?
One of the glasses, when you side, you have like your right side, your left side, and your left side.
Okay? Switch eyes. That way.
Reverse.
Reverse. Something really strange is going on here. Agree? So here's what's going on with these glasses. They have two things in them. One is the polarizer, and one's what we call a quarter wave plate. And what that quarter wave plate does is it makes the light so the polarization in one direction is delayed by 90 degrees, or a quarter of a wavelength, from the polarization in the other direction. And so as the wave travels, you have the electric field that's in this direction. 90 degrees later, it's in this direction. That is half a wavelength or a quarter wavelength later. And if you do the math, you have your electric field is now doing a circle. It never goes to zero, it just goes in a circle. Sometimes it's zero in the horizontal, sometimes it's zero in the vertical. You can get that. So. Or you can play, no, it doesn't. And so we call this circularly polarized light, and you can make it right circularly or left circularly depending on which direction you retard with that quarter wave plate. And so what they're doing with the projector is they're projecting two completely separate pictures. One of them with light that's circularly polarized left, one that's circularly polarized right. And then you have these that will put the quarter wave plate to bring it back together and then block one orientation or block the other. So that way your right eye always sees just the camera that's intended for the right eye. The left eye only sees the light that's intended for the left eye. Now, how many people have gone to watch a 3D movie at Henry Dorley Zoo in Omaha? They don't give you these glasses, do they? What do they give you? They give you glasses that today's movie stars would wear. Things that have these big Herkin lenses. And those lenses are this. I could go there and I could not pay their fee. And I could hold it like this and like this. And I could watch their 3D movie without paying for the 3D glasses. Because they have one projector that's giving vertical polarization, one that's giving horizontal polarization. And once again, we see one thing with one eye and one in the other. Don't be laughing at my style, man. This will come. I mean, you've seen how big glasses are. This will come in style. The problem is, with this, what happens if you rotate your head? You're going to get some of the light from both the projectors for each eye. So you lose your 3D effect if you rotate your head too much. Whereas with the circular polarization, the right eye always sees what's supposed to be seen by the right eye. So if you turn your head, you still have the picture you're supposed to see. Now, you still do lose some 3D aspect because the pictures are assuming that you're on a horizontal plane with your eyes, and it's making images so they, cross each other closer or farther. That's how they get the 3D. Well, when you turn your head, they're going like this. And so that's going to be not quite lined up. But polarization is a big key for today's 3D. If you were going to old school 3D, the oldest school 3D is you have one red lens and one green lens. And so the picture actually, one has more red and one has more green, and it uses those colors to guide the eyes for saying the 3D. It's not a very good 3D mechanism because it messes with your color perception, but it's something that works. And I think I told a few people the Pulfrung effect, the fact that if you have less light, your eye's frame rate drops so you don't see things quite as quick. That's been used. Married with Children used it. They had a special 3D episode, and they had things like everything's going to the left in the screen. And if it's going to the left and you're wearing your glasses, one eye is delayed and it looks like it's closer to you. If it's going to the right, it looks like it's farther away. That's really, really cheesy 3D. But you know what Married with Children was? Cheesy. One of my classmates in college actually worked on that show. And then Gilmore Girls. Yeah. So, moving on. Linear polarization is the only polarization that you're going to be responsible for. That's the one you're going to be testing in lab today. So you have two tests, two hypotheses. One hypothesis is the one on the diffraction from a diffraction grating. The other hypothesis is what we call the law of Malice that we'll introduce in just a moment. So, remember I talked about the electric field vector can be broken up into components. And if I have a polarizer, and the polarizer is only allowing, let us say, vertical polarized light through, and my light is polarized in this green direction, only the EY gets through. How big is the EY here? It's what? Okay, so that's going to be E sine theta. And the EX will be E cosine theta. Now for convention, we actually measure the angle from the polarization axis, so we're actually measuring the E cosine theta by convention. And so if I have a polarizer, and the polarizer is vertical, and then I put a second polarizer, and the polarizer is like this, then the angle between these two, let's say that's theta, the amount that's parallel between the black and the green is going to be the cosine of the angle, right? Because that's the adjacent side. And so what I would have is the electric field. I start with some light that's polarized in all directions, right? And it comes through, and after going through, I have only vertical polarized light. And I'm going to say that has an electric field of E1. When I go through the second one, what direction is it going to be polarized when it goes through the second polarizer? In the direction of? The second polarizer, right. I just want to make sure you're following along with what I'm doing here. So it's going to come out like this, and it'll have E2, But the electric field 2 will be electric field 1 times cosine of the angle between the two polarizers. Now, the intensity of light, the thing that we interpret as how bright it is proportional to the electric field squared. So intensity 1 is proportional to electric field 1 squared. Intensity 2 is proportional to electric 2 squared. And as we did earlier in the lecture, I could put this as equal to C E1 squared equals C E2 squared. But using my equation here for E2, that's equal to C times E1 squared cosine squared of theta. But what is CE1 squared? Intensity 1. So I have intensity 2, and I ran out of space, so I'm going to write it up here at the top. Intensity 2 is equal to intensity 1 cosine squared of the angle between the two polarizers. This is what we call the law of Malice. Whoops. So there it's written out. This is exactly what I just talked about, except for with nicer drawn pictures. And so I wanted to get to this so you can see how Malice is spelled. M-A-L-U-S. It's a dude's last name. It's not Malice. It has nothing to do with forethought either. So if you have an ideal polarizer, you should have the polarized light that goes through the second polarizer is the intensity that went through the first one times cosine squared of the angle between them. Now let me go back 17 slides. Okay, not that many. What if it's unpolarized light and it goes through the first polarizer? So like when I held the single polarizer up. In that case, I had unpolarized light, which means I have light of all different angles. Then I have to add it all up. Well, using calculus, you can integrate it up. It's not hard. Without calculus, we just drop to the answer. And that is, okay, where is it? 1/2. If you have initially unpolarized light and it goes through a single polarizer, half of the light gets through. So if you start with unpolarized light and put a polarizer, just remember, half. If then you put another polarizer, it depends on the angle between them. And so when I did my example with the 3 polarizers, I had a 45 degree for the middle one and 90 for the last one. So if I draw that picture, I had a polarizer like this, a polarizer like this, and a polarizer like that. And so if I have intensity I0 coming into the first polarizer, how big is I1? 1/2, because it went from unpolarized to polarized. Now it goes through with an angle of 45 degrees. How much gets through the next one? It turns out it is, but I want to put it in equation form. It's going to be I1 cosine squared of that angle, which was 45 degrees. And then how much gets through the last one? I3 is equal to I2 cosine squared of 45 degrees. Now in this case, cosine of 45 is the square root of 1/2. So cosine squared of 45 is 1/2. And so it turns out that this is I1 is equal to 1/2 I0. I2 is equal to 1/2 I1. I3 equals 1/2 I2. Put that all together and you get I3 equals 1/2 of 1/2 of 1/2 I0 equals 1/8 I0. Now I did this example in class last year and I asked a question on the test and it had 30 degrees instead of 45. So of course the pictures have to change as well. And it even had a picture. What do you think happened on the test? About half the students said 1/8. But if it's 30 degrees between them, Then you have cosine of 30 degrees. Anybody know what cosine of 30 degrees is? Square root of 3/4. So if you square it, it's 3/4. So in that case, it's 1/2 times 3/4 times 3/4, 9/32. A lot of people didn't actually look at the angles and just said, oh, it's 1/2 every time, because it had been 1/2 in my example. So this time I changed it to 30, so you remember you have to actually look at the angle between the polarized light and the polarizer. So you've already seen the example here. Don't need to go through that again. Problem-solving strategy when you're doing problems with polarizers. For the homework that is due on Wednesday, you don't have this stuff covered, but if the homework is due on Friday, you will. So you will have problems with this and the stuff from the first half here. So as you work problems, remember the transmitted light is linearly polarized along the polarization axis of a polarizer it goes through, regardless of what direction it's polarized before it came in. Right? The polarization before you start affects how much gets through, but the direction when it comes through is always based on the polarizer. By the way, if you use two polarizers, often we'll call the first one polarizer and the second one an analyzer, because it's analyzing the polarization. Okay, number 2, remember the rule that if it's unpolarized and goes through polarizer, half of the intensity gets through. And then number 3, the law of Malice. That's all there is to doing problems with polarizers. Pretty simple, until you do all the cool stuff I did with my demonstrations. Then it gets more complicated. So we've already answered this question. We can move on. Get to cool things. I saw Jordan playing with his, I thought at least, playing with his phone or calculator. Your phone or calculator uses a liquid crystal diode display. What's a liquid crystal diode? Well, liquid crystals are a special category of materials that are in liquid form but have a crystalline type of structure, right? Repeatable structure. And what's really cool about those liquid crystals is that they rotate the polarization proportionally to the voltage difference you put on them. So you change the voltage and the polarization gets changed. So how you make an LCD display is you have the light that comes in. So the front of this has light coming in. Now some have a backlight. It's a slightly different thing, but same idea. Light comes in, goes through a polarizer, and then you have the liquid crystal. And so let's say it goes through the polarizer and it's like this. Then the liquid crystal, depending on the voltage, will either rotate it like this, or, well, actually rotate it by 45, or rotate it by 90. Hits a mirror and reflects back. Either continues to rotate by 90 or continues to rotate by 45. If you rotate by 45 each time, what's the total rotation? 90. Is it going to get out? If you rotate the light a total of 9 degrees, so it was like this, and you rotate it to this, by the time it comes back to getting out? Nope. So that doesn't get out. That's dark. If you rotate it 45 and then another 45, that's what I just said. If you rotate it 90 the first time and then another 90, then it will be coming out. And so it depends on how much it gets rotated. And so it depends on the voltages. And so, of course, they make it so it's going to be light if there's no voltage. And then you put a voltage and it rotates to an angle where it's going to be blocked. So these are using polarizers to make a cheap display, which, once again, is physics and totally cool. Last thing, sky. I know you guys aren't the ultimate nerds that I am, but I used, until a student sat on my glasses when she came for help in my office, I used to have these really expensive prescription glasses that were sunglasses, polarized, all 9 yards. And so I would be like driving down the road, and I look at the road, and I would start going, and grin like an idiot. Not because I am an idiot. I don't think I am. But I love it because when light reflects, well, the light has electric waves, electromagnetic waves, and the electric fields, if it comes and hits the surface like this, the electric field will bounce off. It'll reflect. But if it hits like this, it'll transmit. And so you get a preferential reflection. It's preferentially polarized. So the glare, the light that reflects off of the surface, tends to be polarized parallel to that surface. So when I'm looking at the light reflecting off the road, the glare, the sunglasses are made so that they're going to block horizontal light, allow vertical. And so if I stand with my head straight up, it should be blocking that glare, and the road looks darker. But if I rotate to the side, now it's allowing the glare through, and it looks brighter. I do the same thing when I go to the beach. I do that for a while, and then I say, to my nephew or my son, here, put these on, check it out. Isn't that cool? Because you have polarization that occurs naturally on reflection. Before these were invented, scientists made polarizers by utilizing that reflection. I should mention how these are made. It's a polymer. They pour the polymer, and then they stretch it. And when it stretches, it gets these little fissures. And then they put polar molecules on there, and the polar molecules line up with the fissures. Well, why do they do that? Those polar molecules, when light hits it, the electrons will oscillate in the direction of the polar molecule, and it'll absorb the light. But if the light is like this, it can't oscillate that way because they're lined up like this, and it goes through. And so that's how these are actually made. It's a cool process, pretty ingenious. Not something I would have thought of. The sky is the one that's on the screen. The sky also polarizes the light. We have sunlight. Sunlight is unpolarized. You have an electric field going in all directions, except for the direction the light's traveling. If the light comes straight to you, that is, if you look straight at the sun, you're going to be seeing this unpolarized light. But if you look somewhere else, you're only seeing scattered light. You're seeing light that's scattered due to Rayleigh scattering, the same Rayleigh from the Rayleigh's criterion. And that Rayleigh scattering says that the efficiency of the scattering is proportional to 1 over wavelength to the 4th power. So something with a shorter wavelength is far more efficiently scattered. What color's got the shortest wavelength? Blue or violet, yeah, but I always discount violet. You are correct. Just want to make sure we're clear on this. So when you look at the sky, you see blue because that's the light that's scattered the most. When you look at the sun, you got the blue missing and the yellowish color. So you have that scattering, but that scattering, you had light that was randomly polarized, comes out in a different direction, and the new polarization has to be perpendicular to the direction that it's traveling, as well as perpendicular to the original direction. Perpendicular to the original direction because you start with your light with electric fields only in directions perpendicular to the motion. And then the scatter, you have light still perpendicular to the motion, so it's perpendicular to both. So you can see that if you're looking at sky that's a 90-degree angle from the sun to the piece of the sky you're looking at to you, it's going to be perfectly polarized. Now keep in mind, there's also going to be sunlight that goes like this. It's never going to be perfectly polarized because you'd have, some differences, but you can get different polarizations at different angles in the sky. So I, once again, wearing my polarized sunglasses, look up at the sky and go, look, brighter, darker, because physics is awesome. Okay, let's get to the lab. I had lectured for an hour and a half. Fortunately, your experiment, like last week, they're both very short. I don't tell you how to do it, but you need to measure 2 things. One is a test that would test or disprove the diffractions we talked about, d sine theta is equal to m lambda. And an outcome you need to get from that is the wavelength of the helium neon laser. The second thing is a test of the law of Malice. And with your test of the law of Malice, do not just do 1 or 2 angles. Do a large number of angles. I recommend doing 0 degrees, 10 degrees, 20 degrees, 30 degrees, 40 degrees, 50 degrees, 60, 70, 80, 90. So you can see a full play out of what's going to happen. For your light source and testing the law of Malice, just use this. You'll need to have 2 polarizers. So you have 1 polarizer here. Notice you can change the orientation, so make it so the 0 is on the indicator for the first one. That way, the other one reads this angle between them. Make sure you get these things square with each other. Then the second one, you're just going to adjust the rotation here and measure what the angle difference is and measure how much light gets through. You measure how much light gets through with this. This is a light level sensor. When you plug it into the computer and start Data Studio, it should recognize it. So you're still using Data Studio, but you're not even using the Pascal interface. This just plugs into the computer. And so it will measure the light here. You have 3 sensitivities you might need to change. Obviously, we need to turn the lights off in the classroom for you to do this. You want to place it so it's not going to move, and the light hits this that's going through the 2 polarizers. Okay, I do want, by the time you leave, to give me these back again. I encourage students to play, so I'm leaving them with you for now. But I want them back. Any questions before you start?